In the video of endo versus exo, we already saw some stereochemistry of the dienophile, but I wanted to do one more example. And over here on the left is our diene, and on the right is our dienophile. And we can see that this time our dienophile is trans in terms of the substituent across my double bond here. So I have a trans dienophile, and in the other video we did a cis dienophile. If I take these two molecules together and heat them up, I'm going to get a Diels Alder reaction. So we need to think about the mechanism, and we need to think about the shape of these molecules. So if I look at my diene here, I can recognize that these four carbons, one with the double bonds, are sp2 hybridized, and the carbons that don't have any double bonds, these two right here, are sp3 hybridized. So the carbons that are sp2 hybridized are planar, and so we could think about the diene as being relatively planar. Okay, so I'm sure it has a little bit of movement there, but it just helps us out for the mechanism if we're drawing our diene to try to get our diene planar here. So I'm going to attempt to draw our diene and put a double bond here and a double bond there, like that. And then for my dienophile, if I think about these carbons, right, these carbons are all sp2 hybridized, so my dienophile is planar. So I could think about two planes approaching each other for my mechanism. And so one possible way for these two molecules to approach each other would be for this carboxylic acid group to be over here on the right, and therefore there would be a hydrogen over here on the left. And since it's trans, then I would have a carboxylic acid over here, and then a hydrogen over here, like that. So let's think about what happens in the mechanism, right, which we've gone over before. The electrons in red here are going to form a bond, right? They're going to move into this space, and it's really hard to see because this carboxylic acid group gets in the way. But we've seen how a bond is going to form between this carbon and we have to go all the way over here to this carbon, right? So that's where our bond is going to form. And then we had our pi electrons in blue. Right, the pi electrons in blue are going to move into here to form a bond, and once again we have a long distance between these two carbons, so it's this carbon which is going to be connected to this carbon. And then finally our electrons in magenta, these electrons right here, are going to move, and those electrons are going to move into here, like that. So if I highlight those electrons on my drawing down here, right, these would be the electrons in red. And I'm going to form go ahead and put the electrons in blue, right? So I could say these would be my pi electrons in blue, and then my pi electrons in magenta are right here. And when we think about it, we're going to form a bond between this carbon and this carbon, so a shorter distance to go this time, and then this carbon and this carbon right here. So when I think about the next step, right, I know I'm going to form a bond between those sp2 hybridized carbons, and those sp2 hybridized carbons are going to rehybridize to form sp3 hybridized carbons. And when they do so, we're definitely going to get the carbons in magenta are going to be pushed up in space. So let me go ahead and draw what we get. Right, so the back here, and then we get the carbons pushed up in space. Those two carbons are pushed up in space like that, and we get a bond that forms between what used to be our diene and our dienophile. And because this is a concerted 6 pi electron transition state, the stereochemistry of the dienophile is going to remain the same, meaning we're going to still have a carboxylic acid group right here, and we're still going to have a hydrogen over here. We're still going to have a hydrogen right here and a carboxylic acid over here, like that. And we're also going to form a double bond like that. Let's show where those electrons went, right? The electrons in red went here. The electrons in blue went here. And the electrons in magenta went right here. And then also these are the two carbons that flipped up in space to form our bridge bicyclic compound here. So when I redraw this, so we can see our bridge bicyclic compound a little bit better and look at the stereochemistry, right? I could draw my bicyclic molecule like this, and when I focus in on this carbon, which is this carbon in blue, I can see my carboxylic acid group is going to be up relatively, right? So that carboxylic acid is up, and then this hydrogen here would be down. And then when I look at the stereochemistry and the carbon in red, this time I have a hydrogen up and my carboxylic acid group would be down. So I can go ahead and show my carboxylic acid group as being down like that. And then, of course, I still have my double bond here. So this is one possible product. And notice, once again, our stereochemistry. We had a trans dienophile, and in our product, our carboxylic acid groups remained trans to each other, right? This group is going up relative in space, and then this carboxylic acid group is going down relative in space. So it's still trans in our product. So stereochemistry is preserved. I could have shown my dienophile approaching from a different direction, right? So that's possible as well. So let's go ahead and do the same mechanism, except this time I'm going to show the dienophile approaching from a different different orientation here. So I'm going to go ahead and redraw my diene, put in my electrons like that. And this time, my dienophile, I'm going to say it approaches the molecule like this. So instead of the carboxylic acid group being on the right, I'm going to put the carboxylic acid group on the left, and so therefore there'd be a hydrogen here. Since I have to maintain my trans stereochemistry, this time this carboxylic acid group would be over here, and a hydrogen would be on the left. All right, so same thing. Let me identify my electrons. These are my electrons in red. These are my electrons in blue. And these are my electrons in magenta, like that. And when I form my bonds, I'm going to form a bond between this carbon, and then this carbon and this carbon over here. So let's go ahead and draw the product, right? So once again, I'm going to get those two carbons in the center are going to flip up, and I'm going to form my bicyclic compound. I'm going to form bonds between what used to be my diene and my dienophile like that. And at this carbon right here, it gets rehybridized to form an sp3 hybridized carbon, but the hydrogen is still going this way. The carboxylic acid is still going this way. And at this carbon right down here, my carboxylic acid is still going to the right, and my hydrogen is still going to the left, and I formed my pi bond right in here. So once again, follow the electrons. Electrons in red form this single bond, this sigma bond here. The electrons in blue form this sigma bond right here, and the electrons in magenta form this pi bond back here like that. When I go ahead and redraw my product, my bicyclic compound, right, so let's go ahead and redraw it. So I have my bridged bicyclic compound like this, and I go ahead and have this portion of the molecule. So once again, when I think about this carbon now, so now I'm in the carbon in blue, and I can see that my hydrogen is going to be up this time. So my hydrogen is going to be up, and my carboxylic acid group is going to be down once that molecule changes conformation a little bit. So I get my carboxylic acid group going down. When I move over here to the carbon over here on the left, the one attached to the red bond here, I can see this time this carboxylic acid group is going to be up, right? So I can go ahead and show my carboxylic acid group as being up in here. Let's see if I can fit that in. And the hydrogen would therefore be going down. So I have my hydrogen going down. And when I think about the stereochemistry of my dienophile, right, I had trans stereochemistry over here. And when I look at my product, I can see that I have a carboxylic acid group going down at this carbon, and I have a carboxylic acid group going up at this carbon. So they remained trans in my product. And so I get two products for this Diels Alder reaction, and these are my two products. These are enantiomers of each other. Right? So these are these are enantiomers. Let me go ahead and write that in here. So enantiomers, non-superimposable mirror images of each other. And we can see that I have trans carboxylic acid groups in both. So why do we not have to worry about endo or exo here? Well, the reason has to do with, of course, if I look at this product right here, we saw in the endo versus exo video that there's some extra stabilization associated with this carbonyl and with this developing pi bond. So I get some stabilization with the top approach, and I also get some stabilization with the bottom approach. And so because of that, I'm going to get a mixture of enantiomers from my product. In the next video, we're going to look at the stereochemistry of the diene and also think about stereochemistry of the diene and the dienophile together. And that, of course, makes the Diels Alder reaction a little bit harder.